Today we're going to be jumping into ownership and understanding ownership. This is Fight Me. Let's dive in. Alright. Understanding ownership. Ownership is Rust's most unique feature and has deep implications of the rest of the language. It enables Rust to make memory-safe guarantees without needing a garbage collector. So, it is important to understand how ownership works. This is kind of a Rust-centric thing, which ownership is like what makes Rust Rust, okay? We're going to be learning about that today. In this chapter, we'll talk about ownership as well as several related features, borrowing slices, and how Rust lays out data in memory. Okay, what is ownership? Ownership is a set of rules that govern how Rust program manages memory. All programs have to manage the way that they use computers' memory while running. Some languages have garbage collection that regularly looks for no longer used memory as the program runs. In other languages, the programmer must explicitly allocate and free the memory. Rust uses a third approach. Memory is managed through the system of ownership with a set of rules that the compiler checks. If any of the following rules are violated, the program won't compile. And that's why we get so many compiler errors, and then that's why it panics and screams at us and tells us to fix things before it compiles. None of the features of ownership will slow down your program while it's running. Because ownership is such a new concept for many programmers, it does take some time to get used to. The good news is that the more experienced you become with Rust and the rules of the ownership system, the easier you will find it to naturally develop code that is safe and efficient. All right. When you understand ownership, you'll have a solid foundation for understanding the features that make Rust unique. In this chapter, we'll learn ownership by working through some examples that focus on very common data structures, which is strings. And there are two types of strings. We're going to look, I call them a big S string and a little s string. The stack and the heap. This is a very important concept, so pay attention. Many programming languages don't require you to think about the stack and the heap very often. But in systems programming languages like Rust, whether a value is on the stack or the heap affects how the language behaves and why you have to make certain decisions. Parts of ownership will be described in relation to the stack and the heap later in this chapter, so here is a brief explanation in preparation. Both the stack and the heap are parts of memory available to your code to use at runtime, but they are structured in different ways. The stack stores values in order that it gets them and removes the values in the opposite order. Think of a stack of coins. You're going to put them in the specific order that you get them, but you can only take them off in that specific order. You can't take a coin off in the middle of the coin stack. Think of a stack of plates. Oh, here we go. When you add more plates, you'll put them on top of the pile, and when you need a plate, you take one off. Adding or removing plates from the middle or the bottom won't work as well. Adding data is called pushing onto the stack, and removing data is called popping off the stack. All data stored on the stack must have a known fixed size. Data with an unknown size at compile time or a size that might change must be stored on the heap instead. The heap is less organized. When you put data on a heap, you request a certain amount of space. The memory allocator finds an empty spot on the heap that's big enough, marks it as being in use, and then returns a pointer which is the address of that location. This process is called allocating on the heap, and sometimes abbreviated as allocating. Pushing values onto the stack is not considered allocating. Because the pointer to the heap is known, fixed size, you can store the pointer on the stack. But when you want the actual data, you must follow the pointer. Think of it being seated at a restaurant. When you enter, you state the number of people in your group. and the host finds an empty table that fits everyone and leads you there. If someone in your group comes late, they can ask where you've been seated to find you. I feel like I would say that's a pretty good idea. I'm thinking of it like I think of it like a little mountain, and what the directions to the mountain are in a specific spot. Like they have like a little map on the stack, and that map has the coordinates on the mountain. So like you can go to that portion of the mountain and take whatever you need from there, whatever information is on that mountain. That's what I think of the heap. I don't know. It's each their own. Okay. Pushing to the stack is faster than allocating on the heap because the allocator never has to search for a place to store new data. That location is always at the top of the stack. Comparatively, allocating space on the heap requires more work because the allocator must first find a big enough space to hold data and then perform bookkeeping to prepare for the next allocation. Accessing data in the heap is generally slower than accessing data on the stack because you have to follow a pointer to get there. Contemporary processors are faster than if they jump around in less memory. Continuing the analogy, consider a server at a restaurant taking orders from many tables. It's most efficient to get all the orders at one table before moving on to the next table. Making an order from table A, then an order from table B, then an order from table A again, and then one from table B again would be much slower. By the same token, a processor can usually do its job better if it works on data that's close to other data, as it is on the stack, rather than further away, as it is on the heap. That's why I'm thinking of like a stack as like kind of the entryway of this mountain, like this park. So like you see the maps, you have everything in the shop. Like you can kind of just pick what you need there if you need a snack, if you need a drink. But when you're on that mountain, obviously the coordinates from that map are on the mountain. It's just so much further away. You have to walk to it. You have to ride a bike to it, or you have to go on a vehicle to that area on the heap. Okay. Okay. Yeah. When your code calls a function, the values passed in the function, including potentially pointers to the data on the heap, and the function's local variables get pushed onto the stack. When the function is over, those variables get popped off the stack, keeping track of what parts of code are using what data on the heap, minimizing the amount of duplicate data on the heap, and cleaning up unused data on the heap so that you don't run out of space, are all problems that the ownership addresses. Once you understand ownership, you won't need to think about the stack and the heap very often. But knowing that the main purpose of the ownership is to manage heap data can help explain why it works the way it does. So in other languages, they have something called a garbage collector, and I think we already talked about this a little bit earlier, but it was kind of breezed over. Garbage collector helps clean up any unused data. Rust doesn't do that, and it takes a lot of extra compile time and runtime to clean up all that stuff. So it's better, it's safer for you to learn the ownership rules and referencing rules. So that we're going to get into that. First, let's take a look at the ownership rules. Keep these rules in mind as we walk through the examples that illustrate them. Each value in Rust has an owner. There can only be one owner at a time. When the owner goes out of scope, the value will be dropped. Now that we're past basic Rust syntax, we won't include all function main code in the examples. So if you're following along, make sure that you're putting the following examples in the function main manually. As a result, our examples are a bit more concise, letting us to focus on the actual details rather than boilerplate code. As a first example of ownership, we'll look at the scope of some variables. A scope is a range within the program for which the item is valid. Take the following variable. So let s, we're binding it to this string called hello. Now the variable s refers to the string literal, where you're gonna see this a lot, string literal, where the value of the string is hard-coded into the text of our program. So we know how many bits that string is holding within our program, correct? The variable is valid for the point at which it's declared until the end of the current scope. So listing 4-1 shows the program with comments annotating where the variable s will be valid. So this is where it's showing the scope of this variable. How long is the duration of its life? Okay. Within these curly brackets, you will see that right here it says it's not valid here since it's not declared yet. Then we declare our let s equal hello, which is not returning anything. We're just declaring it as a statement. From here, we can do some stuff with s. Okay. Once we move out of this curly bracket, we are out of scope. In other words, there are two important points in time here. When s comes into scope, it is valid. It remains valid until it goes out of scope, which is the end of the curly bracket. At this point, the relationship between scopes and when variables are valid is similar to that in other programming languages. Now we build up on top of this understanding by introducing a string type, and I call this the big S string type because there's two different string types, okay? We have a heap string type and then we have a stack string type. And we're going to be talking about that. So the string type. To illustrate the rules of ownership, we need a data type that is more complex than we covered in data types of chapter 3. The types covered previously are a known size and can be stored on the stack when their scope is over, and then can be quickly and trivially copied to make a new independent instance if another part of the code needs to be using the same value in a different scope. Okay? That was a very long sentence. Sorry. But we want to look at the data that is stored on the heap and explore how Rust knows when to clean up that data. And the big S string type is a great example. So we'll concentrate on the parts of the big S string that relate to ownership. These aspects also apply to other complex data types, whether they are provided by the standard library or created by you. We'll discuss non-ownership aspects of string in chapter 8. Okay, we've already seen string literals where a string value is hard-coded into the program, and that is our, I'll show you what our little string looks like. String literals are convenient, but they aren't suitable for every situation in which we may need to use text. One reason is that they're immutable. Another is that not every string value can be known when we write our code. For example, if we want to take user input and store it. It is for these situations that Rust has a string type, a big string type. This type manages data allocated on the heap and such is able to store an amount of text that is unknown to us at compile time. You can create a string from a string literal using a from function like so. So we have let s, we're binding it to this string literal, which is hello, but we're doing a string, big string, : from hello. The double colon operator allows us to namespace the particular from function under the string type rather than using some sort of name like string _ from. We'll discuss the syntax more in methods section of chapter 5, and we'll talk about namespacing with modules and paths referring to the item in the module tree in chapter 7. Okay, this kind of string can be mutated. So let mute s bind to string : from, and then we have a string literal within the parameter. Okay, now we're doing a push. So we're using S here. We're adding this method. We're adding this. Why is it not letting me? We're adding this method by using a dot. And then within the parameters, we're adding this comma world exclamation point. We're using push string that appends the literal to this string. And then print line string, we're using a placeholder for string, this S. And this will print hello world. So what's the difference here? Why can string be mutated but literals cannot? The difference is in how these two types deal with memory. Let's get into it. How do they deal with memory? Memory and allocation. In the case of string literal, we know that contents at compile time, so text is hard-coded directly into the final executable. This is why string literals are fast and efficient, but these properties only come from string literals' immutability. Unfortunately, we can't just put a blob of memory into the binary for each piece of text whose size is unknown at compile time and whose size might change while running the program. With the string or big string type, in order to support a mutable global piece of text, we can allocate an amount of memory on the heap unknown at compile time to hold its contents. This means that the memory must be requested from memory allocator at runtime. We need a way of returning this memory to the allocator when we're done with our string. Where am I? I'm forgetting my place. That first part is done by us. We call string : from. Its implementation requests the memory it needs. This is pretty much universal in all programming languages. However, the second part is different. In languages with a garbage collector, as we talked about before, that the garbage collector keeps track of and cleans up memory that isn't being used anymore. And we don't need to think about that. In most languages, without a GC or garbage collector, it's our responsibility to identify when memory is no longer being used and to call code to explicitly free it, just as we did to request it. So I'm pretty sure that would be like very low level languages like C. If you're learning like a machine language like assembly, you would have to clean that up yourself because the wasted memory will make your code run longer. It would be an inconvenience to you because you're using more bytes or bits than you really need. So, all right. If we forget, wait. Doing this correctly has historically been a difficult programming problem. If we forget, we'll waste memory. If we do it too early, we'll have an invalid variable. If we do it twice, that's a bug too. We need to pair exactly one allocate with exactly one free. Right. And that's very difficult and an ongoing issue. And Rust, as a newer, I guess, higher level language, as we saw in the last chapter, has eradicated this issue. And that's why we love Rust. Okay. That's why we love Rust. Okay. Rust takes a different path. The memory is automatically returned once the variable that owns it goes out of scope. Here's a version of the scope example in 4-1 showing that string instead of a string literal. Okay. So we have our scope. We're binding S to the string : from within their parameter. We're going to have an argument of hello, which is a string. We do stuff. The scope is now over. It's no longer valid. So after this point, it's no longer valid because we're out of scope. There's a natural point at which we can return the memory of our string, how our big string needs to the alligator. When S goes out of scope, when a variable goes out of scope, Rust calls a special function for us. this function is called drop. And it's where an author of the string, or big string, can put the code to return the memory. Rust calls drop automatically at the closing of the curly braces. So it's just saying that when it goes out of scope, it drops that. It uses drop to automatically invalidate that string or whatever that's previous scope had owned. Okay, note that C++, this pattern of deallocating resources at the end of the lifetime, sometimes called, interesting. Okay, just fun facts. All right. This pattern has a profound impact on the way that Rust code is written. It may seem simple right now, but the behavior of the code is unexpected in the more complicated situations. When we want to have multiple variables use the data we've allocated on the heap. Let's explore some of those situations now. Okay. Variables and data interacting with news. Interesting. Multiple variables can interact with the same data in different ways in Rust. Okay, listing 4-2 shows an example using an integer. So we're doing let x bind to 5, an integer, and then we're doing another statement where we're binding y to x, which is our previous variable. We can probably guess what it's doing. We're binding the value of 5 to x, this is what I literally said, and then make a copy of that value in x and bind it to y. Now we have two variables where y and x are both equal to 5, and this is indeed what is happening because the integers are simple values with known fixed size, and these two 5 values are pushed onto the stack because we know what they are. It would be different if you remember from our chapter 2 where we're doing our guessing game. We actually had to use this big S string literal to get user input from our terminal, and we obviously had a standard input IO module being imported, but we didn't know what the size of that that user input would be, so we had to do a big string : new, and then parentheses after that. And that's essentially what it is. We were putting that string onto the heap. Okay, we were pointing from the stack to the heap to allocate that memory. Okay. So let S1 equal big string : from hello, and then we're letting S2. I just wanted to see if it did anything. Okay, it doesn't have any output. I just want to see if it did anything. Okay, so, and then we're binding S2 to S1. Okay, this looks very similar, so we might assume that the way it works would be the same. That's why I try to run it. I was like, wait a minute, this looks a little sketch. That is, the second line would make a copy of the value of S1 and bind to S2, but this isn't what quite happens. Take a look at figure 4-1 to see what happens in the string or big string under the covers. A string is made up of 3 parts, shown on the left: a pointer to the memory that holds the contents of the string, and a length and a capacity. This group of data is stored on the stack. On the right is the memory on the heap that holds its contents. Okay. So this is the pointer. I guess it's the length. Capacity is the same, and you can see that this length is 5 because it's hello. So remember, when we index, we always start at 0, and right now it's going to end at 4. So if we do index this specific value, we would start at 0. Okay. This is the heap. and this is the stack. The length of how much memory in bytes the contents of the string are currently using. The capacity is the total amount of memory in bytes that the string has received from the allocator. The difference between length and capacity matters, but it is not in this context. So for now, it's fine to ignore capacity. Okay. When we assign S1 to S2, the string or big string data is copied, meaning we copy the pointer, the length, and the capacity that are on the stack. We do not copy the data on the heap the pointer refers to. In other words, the data representation in memory looks like figure 4-2. Let's see. So we're copying this value, this onto the stack. Okay, and they're both pointing to the heap. That's what it's saying. We're assigning S1 to S2. The data is being copied, so this is now S2, meaning that we copy the pointer and the length of the capacity that are on the stack. And then this is pointing to the heap because we have our pointer. Okay? The representation does not look like figure 4-3, which is what memory would look like if Rust instead copied the heap data as well. If Rust did do this, then the operation to S2 and S1 would be very expensive in terms of runtime performance in the data on the heap. What? If the data on the heap were large. Me and my literary skills. Honestly, this is actually helping me learn how to read better. Because I'm not a good reader. Anyway, it's technically saying that if we had copied it like this, or if Rust had copied what we had done like this, we would have 2 allocated spaces on the heap, which would be a lot more expensive in runtime in allocation space, of course. So they don't like that. Earlier, we said that when a variable goes out of scope, Rust automatically calls a drop function and cleans up the heap memory from the variable. Okay? In figure 4-2, it shows both the data pointers pointing to the same location. This is a problem. When S2 and S1 go out of scope, they will both try to free the same memory. This is shown as double free memory error. Okay? And this is one of the memory safe bugs we've mentioned previously. Freeing memory twice can lead to a memory corruption, which can potentially lead to security vulnerabilities. Ooh. But they have a solution. To ensure memory safety after the line let S2 equal S1, Rust considers S1 as no longer valid. Therefore, Rust doesn't need to free anything when S1 goes out of scope. Check out what happens when you try to use S1 after S2 is created. It won't work. Oh, here. You'll get an error like this because Rust prevents you from using invalidated references. Okay, so this is our error. Let's look at it. Let S1 string from hello, blah, blah, blah. This is a string type. It does not implement the let S2 equal S1. Value is moved here. Then borrow the value borrowed here after move. So it's been moved and then it's been borrowed. It doesn't like that. It says let S2 equal S1 dot, and this is a new method, dot clone. Dot clone is a very good method because we're now cloning what we were kind of shadowing before. Okay, or copying. If you've heard of the terms shallow copy, and deep copy while working with other languages, the concept of copying the pointer length and capacity without copying the data probably sounds like making a shallow copy. Because Rust also invalidates the first variable, instead of being called a shallow copy, it's known as a move. In this example, we would say that S1 was moved into S2, so that what actually happens is shown in figure 4-4. So this kind of becomes invalidated. S1 is now S2. Although they're pointing to the same heap that it's allocated on here, this kind of becomes invalid because it's such a shallow copy. Now that solves our problem with only S2 valid. When it comes out of scope, it alone will free the memory and we're done. Okay? Oh, okay, I guess this is representation in memory after S1 has been invalidated. Oh, okay, this is the deep copy. So we're cloning right here. So this is a clone of this one. So this one's only going to free up this memory. Oh, okay. Sometimes I don't read raving ahead. I'm nice to be talking. Don't come for me, okay? In addition, there's a design choice that's implied by this. Rust will never automatically create deep copies of your data. Therefore, an automatic copying can be assumed to be inexpensive in terms of runtime performance. Always clone. Don't copy. Just clone. You don't need to move stuff. Just clone it. That's what we're getting from this so far. Okay. Let's do a quick water break. I get thirsty. Okay. Whew. Sorry. Sometimes you just need to take a break from reading. It's just a lot of reading. You know? Okay. Scope and assignment. The inverse of this is true for the relationship between scoping, ownership, memory being freed via a drop function as well. When you assign a completely new value to an existing variable, Rust will drop and free the original value's memory immediately. Consider this code, for example. Let mute s equal string : from hello, which is a parameter or argument within string, and then we're doing another thing, which is s equals string : from ahoy. Ahoy? Okay. From ahoy. So we're using the same variable and creating, I guess, a new, or assigning a new string to that variable. And then we're print lining that s variable right here, and putting world after. So it's gonna say hello world or ahoy world. You know what I mean? We don't know. Now, oh, this one can run. I'm just gonna run it after. Okay. We initially declared a variable s and then bind it to a string with the value hello. And then we immediately create a new string with the value ahoy and assign to s. At this point, nothing is referring to the original value on the heap at all. Figure 4-5 illustrates the stack and heap data now. I kind of want to see. Okay, so it says ahoy world. I think it's because yeah, the original string thus immediately goes out of scope. Rust will run the drop function on it and its memory is freed. When we print the value at the end, it will be ahoy world. Because this is now s. And we let it be mutable. Okay, so then this becomes the new s, ahoy world. Okay. We're almost done. Okay, variables and data interact with clone. If we do want to deeply copy a heap data of the string, not just on the stack data, we can use a common method called clone. We were talking about this earlier. Okay, so we'll discuss method syntax in chapter 5, but because methods are a common feature in programming languages, you've probably seen them before. So here's an example of clone method in action. So we're going to bind s1 to a string from hello, clone from hello, and then we're let s2, and we're going to clone s1, and then we're printing s1 and we're printing s2. We should be getting the same hello and hello. So s1 equals should be hello, and then this one should also be hello. See? And this works just fine. It explicitly produces the behavior shown in figure 4-3 with the heap data, where the heap data does get copied. When you see a call to clone, you know that some arbitrary code is being executed and the code may be expensive. It's a visual indicator that something different is going on. I'd say if you do need to copy anything, use the clone method. Rather have expensive allocation of data than your code panicking and erroring out. So we don't want bugs in the code. Just use clone. Okay, stack only data copy. There's another wrinkle that we haven't talked about. This code uses integer. I can't talk. Sorry, forgive me. Okay, this code using integers, part of which was shown in listing 4-2, works and is valid. So let x equal 5. We're doing a let y equal x, so we're binding y to x, and then we're going to print both of them, and we're going to see how they work. They should work just fine because we know what the integer is. The string or big string is because it's on the heap. So when we're using stack, it's so much easier to copy or do shallow copy. It won't panic the same way it would be if that memory was on heap. I hope that makes sense. We're going to read more about it. So, but this code seems to contradict what we just learned. We don't have to call clone, but x is still valid and wasn't moved into y. Yeah. The reason that these types, such as integers that have a known size at compile time, are stored entirely on the stack, so copies of the actual values are quick to make. That means there's no reason we would want to prevent x from being valid after we create the variable y. In other words, there's no difference between the deep and shallow copying here. So call clone won't do anything different from our usual shallow copying, and we can just leave it out. It's unnecessary. Rust has special annotations called copy trait that we can place on types that are stored on the stack as integers are. We'll talk more about this in chapter 10. If the type implements the copy trait variables, if the type implements a copy trait, variables that use it do not move, but rather are trivially copied, making them still valid after assignment to another variable. Okay. Essentially, what we just learned doesn't apply to what's on the stack, so you don't have to use that. Me forgetting where I am constantly. Okay. Rust won't let us annotate the type of copy, type with copy if the type. Whoa. I don't know what's wrong with me in reading today, okay? Rust won't let us annotate a type with copy if the type or any of its parts have implemented the drop trait. If the type needs something special to happen when the value goes out of scope, we add the copy annotation to the type. we'll get a compile time error. To learn about how to add the copy annotation to your type to implement the trait, see the derivable traits in Appendix D. I'm positive we're going to see this trait later on. So if you do want to go dive into Appendix C, go ahead. You have free will. So what types implement the copy trait? When you check the documentation for the given type to be sure, but as a general rule, any group of similar scalar values can implement copy, and nothing that requires allocation or is some form of resource can implement copy. Here are some of the types that can implement copy. Okay. Integer types: i32, i64, u32, u384, u8, all those fun stuff. Okay. Boolean types is a true and false. Remember, we did them in the last chapter where we're talking about booleans. Floating types, f64, x32, f32, all that fun stuff. Char, tuples. So pretty much everything we learned except strings. Okay. We haven't learned about enums. We haven't learned about structs yet. We haven't learned about hash maps. That is further in the book. But so far, pretty much everything we learned in chapter 3, can be utilized as that. Okay, but it says all, but not i32 and string, because tuples can have multiple data types within its parameters, so you can't have a string in there. It would only have to contain the following in here. Okay. Ownership and functions. The mechanics of passing a value to the function are similar to those when assigning a value to a variable. Passing a variable to a function will move or copy just as the assignment does. Listing 4-3 has an example with some annotation showing where variables go into and out of scope. Whew, this one's long. Okay, so we're doing a function main. Okay, we have let s equal string : from. We're having our parameter hello within this variable. So s comes into scope, takes ownership. Oh, this is what I get for not reading all the way through. Okay, let's go down here first. So we got two helper functions. We have function takes ownership and we have function makes copy. So for takes ownership, we have a parameter of some string. Remember I told you that usually our parameters, you're going to see them at the beginning within these parentheses. And it's kind of like a coin slot. We don't know what some string is. We don't know what string it is or what it has in, you know what I'm saying. Okay. We just know some string is going to return a string. Okay. Print line, and this is our sum string. That's from here. Here, sum string goes out of scope and is dropped. It's called the backing memory is free. Now we go to our next function because this scope is completed. Function makes copy, some integer, so we have another coin. We know that it's going to have an integer or we're going to return an integer later on. Some integer comes into scope. We print line some integer, which was our parameter, and then it goes out of scope. Then we go to our main function. Then we have s bound to a string, from with the parameter of hello. Comes into scope. Now we have takes ownership. We have this function come into scope as well, and it's holding that parameter of s. I'm pretty sure the string is going to be hello. Okay, and then we have another thing that comes into scope, which is let x equal 5. So we have an immutable variable that's holding an integer, and then we call makes copy, which is over here, with our parameter, which we said it was going to be in I32, which is x, which will be 5. So we can run this. Let's see if it runs. So we get hello, and we get 5. Simple stuff. If we try to use s after the call to take ownership, Rust would throw a compile time error. These static checks prevent us from making mistakes. Try adding code to main that uses s and x to see where you can use them and where the ownership rules prevent you from doing so. Return values in scope. Returning values can transfer ownership. Listing in 4-4 shows an example of a function that returns some value with similar annotations as those listed in 4-3. Okay, let's see. So we're not going to look at main yet. We're going to look at. Ooh, my glasses are like behind my headband. It's hurting maybe the poor ear. Okay. Alright, so we're going to be looking at this helper function. So gives ownership is going to return a string. We have no parameters. This is the start of our scope. So gives ownership will move its return value into the function that calls. Within our scope, we have let some string bound to string : from with the parameter of yours. And then, so some string comes in the scope, some string is returned and moves out of calling the function. So remember, when we have returns, there'll be no semicolon. It is just a straight return, an expression. My bad. Okay, and then function takes and gives back. Then we have a parameter of a_string, and then we're going to return a string. Remember, this is our coin slot. We're returning a string, we just don't know what string it is. So, and then we have, this is the argument of a string. Then we're returning that string, and we know that because we have that arrow. A_string comes into scope, and then we are going to use this as a return because it is an expression. Okay. Okay. Where are we? Sometimes I just make this so confusing to read. Function let s1 gives ownership. So this is our gives ownership function. Remember, we're returning a string, and that string is some string. Okay. Gives ownership moves its return value into s1. Let s2 is string : from hello. So s2 comes into scope. Let s3 equals or is bound to takes and gives back, which is s2, which is hello. So take and gives back was going to return a string with the parameter of a string, and we have that here, which is s2, which is hello. So let's run this, and I'm pretty sure gives ownership is going to put yours, right? Some string. Okay, yes, returning some string. Okay, so it's going to be yours and hello. Oh, right, nothing was printed. I only do that. They should have printed that in main so that we can see the return. Anyway, if it was printed or those things were printed, I'm positive it would have shown yours and hello. But they don't like to give us that satisfaction. The ownership of the variable follows the same pattern every time. Assigning a value to another variable moves it. Then the variable that includes data on the heap goes out of scope. then the value will be cleaned up by drop unless the ownership of the data has been moved to another variable. While this works, taking ownership and then returning ownership within every function is a bit tedious. What if we let a function use a value but not take ownership? It's quite annoying that anything we pass also needs to be passed back if we want to use it again, in addition to any data resulting from the body of the function that we might want to return as well. Okay, Rust does let us return multiple values using a tuple, as shown in listing 4-5. Okay, now we have another one. We have another function called calculate length with a parameter of s, which is a string. We are returning a string and a usize, and then we're going to bind length to s, which is here, our parameter, dot length, which returns the length of the string, and then we're using this expression to return. So we're returning s and returning the length. We're going to the main function, let s bound to string, : from, hello. So we have another string, well, we have the string within that parameter. And then let s2 and then length equal calculate length, which is our calculate length, which is s1, which is hello. And we're destructuring. So we want to have s2. Wait, what is it doing? Sometimes I'm reading this, I'm like, huh? I'm pretty sure. So it's let s2, and we're also looking at the length. So we're trying to return both. And then we're trying to return s2 and the length here when we use our print line. So the length of s2, which is 5, this is the length. s2 is hello, and then this is 5 because it's calculating the length of s1, essentially. Whew. Sometimes it can be a little confusing. Code is not easy to read sometimes. But this is too much ceremony and a lot of work for a concept that should be common. Luckily for us, Rust has a feature for using a value without transferring ownership / references. And we're going to do references tomorrow. References and borrowing, and then we have, I'm thinking, the slicing. So we have slicing after that. I don't know how long that one is, but I think we can do references and borrowing tomorrow and our slicing. Just the ownership topic is very, very long, and that's why it took me so long to get through it. I hope you enjoyed this video or this live stream. I have a lot of fun making these, actually. I love reading and I love learning, and it's so hot and sexy to learn and be a little nerd, you know what I'm saying? So I hope you stay tuned for next week's videos. We are going to be starting on Tuesday. I'm doing these streams Tuesday through Thursday, Tuesday through Friday, my bad. And you should come along. You should watch them. I'm sorry about the video in yesterday's stream. In the first 6 minutes, I can see that it was just all wonky, and I'm so sorry about that. I might put that in the comments so that people can